The AsyncTaskScheduler subsystem manages the execution of deferred computations across a pool of worker threads. Tasks are submitted to named queues by client code and processed according to their assigned priority level and scheduling constraints. The scheduler maintains internal state regarding task ordering, worker availability, and queue depth. All operations are thread-safe through mutex-protected data structures. Queue names are case-sensitive strings with a maximum length of 256 characters. Task submission occurs through the enqueue method, which accepts a callable object, optional arguments tuple, and queue identifier. The method returns a task handle object immediately, providing a reference for later status queries or cancellation. In-queue operations append the task to the appropriate queue and increment the depth counter. If no workers are currently idle, the task remains queued until processing capacity becomes available. The default queue is named default if no explicit queue is specified. Worker threads are created during scheduler initialization and persist for the lifetime of the scheduler instance. Each worker thread enters a polling loop, checking for available tasks in its assigned queues. Workers sleep for 100 milliseconds when no tasks are present, then wake and check again. Priority is evaluated by queue order and task insertion timestamp. Workers do not transition between queues. Each worker handles tasks from a fixed set of assigned queues throughout its lifecycle. The task priority system uses integer values from 0 to 100, with 100 being highest priority. Tasks are sorted within each queue by priority first, then by insertion order for tasks of equal priority. Priority is immutable after task submission and cannot be modified through the task handle interface. The default priority value is 50. Priority inversion, where a high priority task waits behind many low priority tasks, is a known characteristic of FIFO-ordered queues and should be considered during application design. Task cancellation is requested through the cancel method on a task handle. If the task has not yet begun execution, it is removed from the queue and its state is marked as cancelled. If the task is currently executing, cancellation is signaled through a separate cancellation flag that the task code must check periodically. Cancellation is not forceful. The task code must cooperate by testing the flag and returning early. There is no timeout for cancellation. The scheduler waits indefinitely for the task to complete. Task execution occurs entirely within the worker thread context. Exceptions raised during task execution are caught and stored in the task handle result object. The exception is not propagated to the calling thread. Instead, it is retrieved through the result method after calling wait. If a task raises an uncaught exception, the worker thread remains alive and continues processing subsequent tasks. Exceptions do not affect queue processing order or worker thread scheduling. The result method blocks the calling thread until the task has completed, then returns the task's result value or raises the stored exception. The wait method similarly blocks until completion, but returns a Boolean indicating success or failure without raising. A timeout parameter may be provided to both methods, measured in milliseconds. If the timeout expires, a timeout error is raised and the task continues executing in the background. Multiple threads may call wait or result on the same task handle simultaneously. Queue statistics are available through the getQueueStats method, which returns a snapshot of queue depth, average task duration, and worker utilization percentage. These statistics are computed at the moment of the call and represent a point-in-time view. Queue depth is the number of pending tasks. Completed tasks are not included. Worker utilization is calculated as the ratio of actively executing tasks to total available workers. Statistics queries themselves do not modify any scheduler state. The scheduler maintains configuration parameters that affect its behavior. Worker count determines the number of worker threads created at initialization. Max queue depth limits the number of pending tasks and causes an queue to block if exceeded. Idle timeout MS controls how long a worker sleeps between queue checks. These parameters are set during scheduler construction and are immutable thereafter. Modifying them requires creating a new scheduler instance. Default worker count is equal to the number of CPU cores on the system. Task timeout behavior is specified per task through an optional timeout MS parameter during in-queue. If a task does not complete within the specified duration, the worker thread does not forcefully kill the task. Instead, a cancellation signal is sent. The task code must respond to the signal to exit early. If the task ignores the cancellation signal, it continues executing indefinitely. No partial results or compensation logic is applied when a timeout occurs. The task execution state remains as it was at the timeout moment. The scheduler supports task dependencies through a depends on parameter. This parameter accepts a list of task handle objects. A task with dependencies remains queued until all its dependencies have completed successfully. If any dependency fails with an exception, the dependent task is marked as skipped without execution. The skipped status is distinct from cancellation and can be detected through the result method. Circular dependencies are not detected. They result in permanent queuing of affected tasks. Callback registration is supported through the add completion callback method on a task handle. Callbacks are invoked when the task reaches a terminal state, either completion, failure, or cancellation. Callbacks are executed within the worker thread context after the task finishes, not on the calling thread. If a callback raises an exception, it is logged but does not affect the task's result or other callbacks. Multiple callbacks may be registered on a single task and are executed in registration order. Metrics collection is performed continuously by the scheduler through internal counters. The getMetrics method returns a dictionary containing task count completed, task count failed, task count cancelled, and average execution time (MS). These metrics are accumulated since scheduler creation and are not reset between calls. To track metrics over a time window, the calling code must poll getMetrics periodically and compute deltas. Metrics queries are constant time operations that do not require locking the task queue. The scheduler shutdown process is initiated through the shutdown method. Shutdown accepts an optional wait remaining parameter. If true, the scheduler blocks until all queued and executing tasks complete. If false, tasks are marked for cancellation and the method returns immediately. Worker threads perform cleanup and exit gracefully. No new tasks may be unqueued after shutdown has been called. Such attempts raise a scheduler shutdown error. The scheduler may be recreated as a new instance after shutdown. Thread safety guarantees are provided for all public methods. The internal queue structure is protected by a single global lock, acquired during enqueue, dequeue, and status queries. Lock contention increases with worker count and task submission rate. The lock is held for minimal duration to reduce contention, typically under 1 millisecond per operation on modern hardware. Deadlock scenarios between the scheduler lock and application code locks must be avoided through careful synchronization, design and client task implementations. Memory management follows standard reference counting semantics. Task handle objects hold references to internal task state. When a task handle is destroyed without calling result or wait, the task's output is retained until the scheduler is shut down. There is no explicit memory limit for result storage. Applications that generate large result objects should be monitored for memory usage. Worker thread stacks are allocated at scheduler creation time and released at shutdown. Total memory consumption grows linearly with worker count and queue depth.